This presentation is delivered by the Stanford Center for Professional Development.
Actually, the first part of the course, I think I hinted at this last time, which is actually quite useful. Everything else so far has just been sort of background, really leading up to this, and it's infrastructure. We're actually now at the payoff point. So we're going to talk about least squares. It's something you've probably seen in a couple of different contexts. And it concerns overdetermined linear equations. So we have a set of overdetermined linear equations. Now here we have y equals ax, where a is, we'll make it strictly skinny. It's overdetermined because you have more equations than unknowns. And of course, for most y, unless y is in the range of a, which if you pick y randomly in Rm is an event of probability 0, you can't solve y equals ax. So one method to approximately solve y equals ax, and it's very important to emphasize here we're not actually solving y equals ax, is to choose x to minimize the norm of this residual. So ax minus y. By the way, some people call the residual y minus ax. It doesn't make any difference because mostly you measure yourself by the norm, and the norm is the same. So the residual is ax minus y. It's the amount by which ax misses y. If you take the norm of that, that's the distance between the point ax and the point y. If you minimize that, that's called the least squares approximate solution. Now, here, I'm going to insist on using approximate. I hate to tell you that on the streets, you would call this the least squares solution of y equals ax. This drives me insane. Because whenever somebody says the blah, blah, blah solution of y equals ax, I presume, in particular, x solves y equals ax. And it's very important to understand in this case, it does not solve it. That's the whole point. It's an approximate solution. Of course, it can solve it. That's possible. And that indeed would be the least squares solution because residuals don't get any smaller than 0, norms of residuals. Okay? So I'll call it least squares approximate solution, but you will hear people, if you look, go to Wikipedia or whatever and type it in, you'll hear people talk about the least squares solution of y equals ax, which is not a solution of y equals ax. So the geometric interpretation is something like this. This is very childish. I can only draw this in R2. In this case, A, of course, is 2 by 1. It's kind of silly. The range of A is a line. So here's the range of A. And here's a point not on the line. And so the question is to find the point closest to this target point y that's on the line. And there's a name for that. When you find a point in a set closest to another point, the point in the set closest to a given point, that's called the projection of the original point on the set. So here AXLS is the projection of y on the range of A. So, and people use all sorts of, you'll see all sorts of notation for that, but maybe the most standard would be this, would be that. So AXLS would be a projection of this point on that set. So that would be probably, if you looked at 10 books, you'd probably see this in 8, something like that, notation. Okay, so that's the geometric interpretation. Let's work out what it is. It's not too complicated to actually just work out a formula for it. So A is full rank and skinny. That's our assumption here. And what we need to do is minimize the norm of the residual. Well, that's the same as minimizing the square of the norm of the residual. The square of the norm of the residual is R transpose R, and you simply plug in what that is, and you get the following function here. Now, that's a constant. That's the norm of y squared. That's a linear function of x, and that's a quadratic function of x, a pure quadratic function of x. The whole thing altogether is called a quadratic, is just a quadratic function of x. This is actually called a quadratic form, the pure one. How do you minimize this? Well, we'll set the gradient with respect to x to be 0. And what you find is the gradient of this, I think we had, is that on the current homework? No, it's on the one we just assigned. All right, then if you can, of course, you can work out the gradient yourself by taking the partial derivative of this with respect to xi. But what you'll get is the gradient of this function is 2 A transpose AX. This should look very, very much like the formula in the scalar case. Minus 2 A transpose Y and that's equal to 0 at a minimum, actually at a stationary point. In this case, it's a minimum. This only has one solution. There's only one possible solution of this equation because A transpose A is invertible. It's invertible because A is full rank and skinny. That's one of these basic properties. And that says, so if I reduce the two and put it on one side, these are very famous equations. They're called the normal equations. You'll see why in just a minute. Actually, the picture before explained that. Since A transpose A is invertible, you have this. You have x least squares is A transpose A inverse A transpose Y. So I don't know how many ASCII characters that is. Let's say it's 10 or something like that. Depends how you count, of course. Watch out, because the whole point of overloading notation is that a very small number of characters can pack a lot of meaning. So this looks very simple, looks very innocent. It means a lot. By the way, it's also unbelievably useful. Okay? So it's a very famous formula. You probably shouldn't forget it. You probably won't forget it, because if you look for it, you'll find it in lots of other contexts and classes and things like that. So here it is. It's A transpose A inverse A transpose Y. You can do all sorts of checks here just to scan this and make sure it's okay. You can check things like, well, if you're going to invert something, it should be square. And indeed, A transpose A is square. That's fine. You should check, in fact, that this is full rank. For example, what can you tell me about that? Why not? You're shaking your head. Exactly. This is square, but not full rank. So that's a semantic error, not a syntax error. How about this one? That's a syntax error. That's right, exactly. That was vigorous and violent head shaking, which is the correct reaction to this. So, okay. So there's the formula for it. It's quite simple. Actually, one very interesting thing here is this is actually, it's a matrix, let's call it BLS, times Y. It's linear. So calculating this approximate solution is actually a linear operation on Y. So that's the first thing you note. Now, if A happens to be square, then A transpose A, then it's invertible. A transpose A inverse is A inverse times A transpose inverse. By the way, there's some slang for A transpose inverse. It's not really slang. People write this as A minus 1 and then A minus T. That's not really, that's kind of standard. That's what this is. And then if I multiply on the left by A transpose, let me do that. A transpose, I get this, and you get A inverse. Okay? So you can see that when x is square, this gives you, this is just a pedantic and silly, complicated formula for the inverse again. So you can think of this as actually a generalization of the inverse, and you'll want to think of this as a generalization of the inverse of A. Now watch out, because in this formula, A is not square. But if A were square, this would reduce to the inverse of A. Okay. Of course, this calculation here is completely wrong when A is not square. In fact, you have syntax errors already here, right here. Okay. Now, suppose that there is, if Y is in the range of A, that means there is an x that solves AX equals Y. In this case, it turns out x least squares is it. Okay? How do you know that? Well, just actually by the definition. X least squares minimizes the norm of AX minus Y over all possible x. But if there exists an x for which AX equals Y, then this thing can be as small as 0. You're not ever going to do any better than that, so that x has got to be x least squares. That's a good property of an approximate inverse to have. Right? Or a method that gives an approximate solution is when the equations actually have a solution, it will return the solution. Now there's a name for this matrix, comes up all the time, and it's called A dagger. So that's a very common, that's universal notation. So it's A with a superscript dagger, and that's called, it's got lots of names. It's called the pseudo-inverse of A, and it's got other names too. If you're British, you'll hear it called the Moore-Penrose inverse, and there's probably some other names for it too. So, and in fact, some people who like long names call it the Moore-Penrose pseudo-inverse. And there's other names. I don't remember them, but they don't matter. Here's what's interesting about it. It is a left inverse of a full rank skinny matrix. So it's this. If you work out A dagger A, that's A transpose A inverse times A transpose, that's A dagger, times A. And I reassociate this way, and I see A transpose A inverse times A transpose A, that's the identity. So you have the following. It is a left inverse of A. By the way, the dimensions of this pseudo-inverse here are the transpose of the dimensions of A. Okay? So if A is skinny, it is in this context, sorry, I shouldn't say if A is skinny. In this context, A is skinny, and A dagger, or A or pseudo-inverse, is going to be fat here. And it's a left inverse. By the way, I could have said this early on. One of the statements on this linear algebra review was that if A is skinny and invertible, if it's skinny and full rank, then it has a left inverse. And I could just have said, here it is, A transpose A inverse A transpose, and you could have just plugged in the formula. But of course, you'd be scratching your head thinking, where on earth did that come from? So that's why I deferred it. So anyway, you now know, here's a very explicit way to construct a left inverse of a matrix. It's just the pseudo-inverse. We're going to find out it's actually not, it should be clear already, it is not the only left inverse. We'll find others, and in fact, we'll find all left inverses soon. Okay. Now, this is, if you want to look at projection on range of A, if you multiply A by XLS, that gives you, well, by definition, it's the point in the range of A that's closest to Y. And it's the projection of Y onto the range of A. That's denoted this way. And that's AXLS. And this is that the projection function is actually linear, and it's given by this matrix here. It just multiplies by that matrix. And that is an M by M matrix. That's what it does. It's a very interesting matrix. By the way, it's pretty. It's got a nice asymmetry. You've got some A's and some A transpose appearing, and an A transpose A and inverse, and all that sort of stuff. You're actually going to see a lot of formulas like this. You're going to have to get used to checking these very carefully to make sure that they're first past syntax, and then whether they're up to the semantics as well. Okay? So, and if you look at it, it has a look of a matrix that sort of would want to be the identity. It is not the identity, unless, by the way, A is square. In which case, when all the smoke clears, this thing just goes away and it's the identity. Okay? But it's not the identity. It's actually its projection, like that. By the way, this already has lots of uses. It basically says something like, you can actually imagine something like this. You can say, you receive a signal with noise, a vector signal, a bunch of, say, a multiple antenna communication system. But you happen to know that the signal should lie in a certain subspace, the range of A. You can simply then project onto the range of A, and what you've got now is the closest signal to the one you received, which is sort of consistent, that's in this known range. Okay, so, and this is used. All right. Yeah? Oh, why is A transpose A? So that goes back to my slide, which said that if A is full rank and skinny, then A transpose A is invertible. So I'm referring back there. I'm not showing it. Here. Actually, you could now with the QR factorization. We could actually establish that connection. Okay.
Excuse me.
So this is a matrix you will also see quite often. It's A transpose A inverse, A transpose, and that's called the projection matrix. It's actually a projection onto the range of A. That's what this matrix is. Okay.
Excuse me.
Let's look at a couple of things here. There's a so-called orthogonality principle, and that says this.
Excuse me.
That the residual.
Question. Hello.
Yes.
All this thing that we said is
This is so cool.
Sorry?
This stuff hasn't been used since 1969. Oh my God.
Actually, the next class here is using it so often.
Really?
Yeah.
You mean more recently than 1969?
Yes.
Cool.
Much more recently, like last Tuesday.
Really?
Yeah, really.
That's so cool.
Yes,
okay.
it is.
That's what I didn't know where it was coming from. Anyway, that's okay, no problem. You have a question, I bet.
Yeah, I still do. So all these things that we are saying is about a skinny full rank matrix, right?
Right.
But what if we have a sensor array and it's not full rank? It's really bugging me. If we have a matrix and it's not full rank, what should we do?
Oh, it should bug you. We're going to get to it. So our discussion right now, here's our discussion, is skinny full rank matrices. Why? Because I said so. That's what, for now. I promise you, we're going to talk first. From here, we will talk within, next week, we'll be talking about fat full rank matrices. Then, week or two later, we will talk about what happens when you have non-full rank matrices. But I promise you, we're going to get back to this. By the way, just to warn you, a lot of times when I say that we're going to get back to it later, of course we don't. But in this case, we really are. Okay? So, okay, good. You should. And it's a good question. All right. And by the way, the answer is it's a bit complicated. And that's why we're doing the simple thing first. All right. Okay. So the orthogonality principle says that the optimal residual, that's AXLS minus Y, is this thing. It's A transpose A inverse A transpose minus I times Y, is actually orthogonal to the range of A. And the picture, well, here I don't have to go digging for it. It's right here. That if this is the range of A, and here's AXLS, and here's Y, the residual, like this, is orthogonal to this. Now, to really make this more interesting, you might imagine at least R3. And in R3, the range of A you could make a plane. And then you have a point, and then you have AXLS. AXLS is the projection of that point on the plane. And if you go from that point up, the point on the plane, up to the original point, you're going to get something that's normal to that plane. Okay? So that's the picture. And I mean, it's quick arithmetic to just calculate, R transpose AZ. And you'll see that it all just works out here. I'll let you do it, because it's easy enough to this is just arithmetic to work out. Now, by the way, there's also a way to understand this. In this case, suppose someone said, well, that usually happens, okay? Sure, that happens in the university, but boy, when you get on real life, no, it's not right. That doesn't really happen. And you can have things, we found things where the angle can be 92 degrees. Something like this. There's actually a pretty simple way to know that this can't happen. And I can turn this into a formal mathematical argument, but I don't want to. If someone produced a point that was alleged to be the projection of Y on a subspace, and this residual weren't normal to the subspace, how would you prove him or her wrong quickly? I just wanted a quick geometric argument, which, by the way, would easily be turned into a mathematical argument. What would you do? I can see your fingers are... I'm going to interpret your hand motions, this guy. He doesn't know, actually, I'm talking about him. He's going, okay. But no, what you do is you take this point and simply move it in the direction where your residual is leaning. If you move a small distance in that direction, your angle goes up, and your distance to that point goes down. And you've just proved the other person a liar. Because you've just moved closer. You move closer, and you're still in the range. The original point was alleged to be the closest point, and you just moved closer than the point they had, so it's impossible. So this is a very good... For example, Fourier series and probably other things as well. Okay. Let's make the connection with QR factorization. If A is again full rank and skinny, we can factor it as A equals QR. Now, in this case, Q is, here R is square because it's full rank and skinny. So we write A, which looks like this, as Q, and then R, where this is upper triangular. Like so. Okay? So that's the That's the picture. And the columns of Q are orthonormal. Well, the pseudo-inverse is just this. It's A transpose A inverse, and I'll just plug in for A, QR. So this becomes, A transpose is, of course, R transpose Q transpose. That's here. Q, R. And now you have to be very, very careful with these things. So when the columns of Q are orthonormal, then Q transpose Q becomes I. Okay? So this just goes away then, and you have R transpose R inverse. Now R is upper triangular and invertible because its elements on the diagonal are positive. So it's invertible. In fact, its determinant is the product of the elements on the diagonal, which are positive. So it's invertible. So R transpose R is therefore invertible. In fact, the determinant of R transpose R is the determinant of R squared, because the determinant of R transpose is the determinant of R. So this is invertible, and of course it becomes R inverse R minus T. That's slang for R inverse transpose, which is the same as R transpose inverse. These two operators commute. Times R transpose Q transpose, that goes away, and in the end you get R inverse Q transpose. Okay? So a very, very simple formula in terms of the QR factorization for the least squares approximate solution of y equals ax. And it's kind of weird, and let me give you kind of a complete hand-waving and utterly wrong argument, but as a kind of a, just as a rough idea, it works okay. You say, well, you have A equals QR. If A were square, and Q were square, and R were square, then you would have A inverse is, of course, R inverse, Q inverse. But Q is, in this case, orthogonal. So I could replace Q inverse with Q transpose. Okay, this is if A is square. But now I look at this for a minute, and I say, hey, wait a minute, what if A is not square? Of course, A doesn't have an inverse, so I want some kind of approximate inverse. And I just use the exact same formula, which is R inverse Q transpose. So roughly speaking, the transpose of a matrix with orthogonal columns is something like an inverse. I can tell you're not buying it. But anyway, okay. Well, it was just looked at. Just threw that out there in case that made any sense to you. But I guess it didn't. Now projection on the range of A, that's A transpose A inverse. But we just worked out what all this stuff is. This is just that. So if I multiply A, which is QR, the R's go away, and you get QQ transpose. And now you know what QQ transpose is. It's actually projection on the range of A. Now you know what it is. So let me remind you that last lecture we talked about Q, skinny matrix, actually has to be, because I'm going to assert that the columns are orthonormal. So the columns are orthonormal. That's Q. And in this case, that is exactly the same as saying Q transpose equals I. Okay? And let's make it M high and N wide. It doesn't matter. Something like that. And I mentioned at the time that QQ transpose is not I. And I said I'd tell you later what it is. And this is one of those times where I wasn't lying then, because I really am telling you what it is later, which is now. QQ transpose is not the identity. It's actually the projection matrix. It projects onto the range of these columns. That's what it is. And that's something like, it's sort of like an inverse. I mean, projection sort of gets you as close as you can in the subspace. Now, by the way, if you're in the subspace, it's the same as the identity. Okay? So now you know what happens when you take, for example, 3 orthonormal columns in R10 and call that Q, form QQ transpose. You get a 10 by 10 matrix, and what it is it has rank 3, and what it does is it projects onto the range of those 3 columns. That's what it does. It calculates it takes an argument x, and it returns a y, which is the closest point in the range of those 3 columns. That's what it is. Okay. We can also explain, oh, and I should mention one thing here. Least squares is not, actually you can, and I would even encourage you to do that. In MATLAB, although I mean this is not supposed to be a class about MATLAB, but I'll say just a little bit about that. You are more than welcome to type something like this: inv of A prime. In fact, I would encourage you to do this. This times A prime times, let's say, y. You're more than welcome to type that in. And you will get something up to numerical precision, which is basically A transpose A inverse A transpose y. Okay? Now, in fact, generally, this is not how this is calculated. Okay? So it's actually it's actually calculated using the QR factorization. And again, this is not I'm not talking about MATLAB here. I'm talking about how people do numerical calculations, which is not what this class is about, but I thought I'd mention it. So you have to distinguish between the formula and then actually how it's calculated. In fact, it's computed typically using the QR factorization. So what would really happen is you would actually do this. You'd form Q transpose and then R inverse here. R inverse, because it's upper triangular, is very easy to carry out. I should mention one thing. This is so common that in MATLAB, this is just this. It's backslash. Okay? And that, I believe, actually is a MathWorks innovation. So it might be just about the only one, but there it is, as far as I know. They were the one that popularized basically to say, A transpose A inverse, A transpose is so important, it should have one ASCII character assigned to it. That's how important it is. And I'm pretty sure that was, in fact, these guys. I mean, you could write this, but, you know, so I guess that would be at least 2 if you type it in text. So that's it. Now, I also have to warn you about this. This does other stuff. So you asked what happens when A is fat, when it's skinny but not full rank. A backslash y will do something. Okay? So be very careful. That's a symbol that is overloaded, and it does not just work out this. It will not warn you, or you'll get very strange warnings and things like that. And it could very happily return an answer, and it won't be what you think it is. So I just mention this. Anyway, there's some notes on the website about this, and you have to read those. Okay. So let's look at full QR factorization. So here you simply extend out the columns Q out to you extend out, you complete an orthonormal basis, and you append on the bottom of R a bunch of zeros. So this now has the same size as A, and this matrix Q1, Q2, although it looks fat because I've separated the columns into 2 parts, is actually square. So this is actually a square matrix. And it's orthogonal. Its columns are orthonormal. Okay. Now, if I take AX minus Y norm squared, this is A. That's the full QR factorization, X minus Y. And what I'm going to do is I'm going to take this expression here, that's a vector in Rm, and I'm going to multiply on the left by the m by m matrix Q1, Q2. That's orthogonal. Now, when you multiply by an orthogonal matrix, you do not change the norm. So I can shove a Q1, Q2 transpose on the left here. I can shove that into both sides. Doesn't affect the norm. Okay? So over here I get this. This is the identity because Q1, Q2 is orthogonal. So you get this. So this is the identity, and I get R1X minus Q1 transpose Y, and the second block entry is 0x, which is 0. It's minus Q2 transpose Y. So this thing is equal to the norm of that norm squared of that vector. But the norm squared of a vector, if you've blocked it out, is the sum of the norm squareds of the blocks. That's what it means. That's what it means. So this is equal to this. Now look at this. Oh, by the way, we haven't solved the problem yet. This is simply a formula for norm AX minus Y norm squared. That's what it is. And so the question is, if you look at this, now we can ask the question, how should you choose X to make this as small as possible? Well, if you look at the right-hand side, it has nothing to do with X. There's nothing you can do about it. So the right-hand side is irrelevant if you're minimizing. Now you want to choose X to minimize this. Well, let's see. How small could this be? Well, it's a norm squared. It can't be any smaller than 0. But it can be made 0. And it can be made 0 by taking X equals R1 inverse Q1 transpose Y. That's our same old formula before. So that's the picture. And the residual with the optimal x is Q2, Q2 transpose, which you can work out directly from this, because that's the residual. So what that means is that Q1, Q1 transpose give you projection on the range of A, and Q2, Q2 gives you projection on the range of A, of the orthogonal complement of the range of A. So that's what this is. This stuff is all very abstract for now, but when we put it in the context of actual applications, I think it'll become clear and possibly even interesting or something like that. Okay, so that's the connection to full QR factorization. Okay. Now we can talk about applications. So basically, we already had the conversation about y equals ax. Frankly, it's a bit of a short conversation. We already had it, and it's good you have it. So the short conversation goes something like this. If you have an inversion problem and you have y equals ax, then if the columns of A are independent, which is to say that A is full rank, I'm assuming it's skinny here, then it says, yes, indeed, in that case, you can reconstruct x exactly from y. What would do it? Well, a left inverse would do it, but you already know a left inverse now, which is, in fact, this A dagger, or A transpose A inverse A transpose. So you know a left inverse. That's this. Okay. Now, generally speaking, there's going to be some small, and even in all cases, in all cases where you actually make measurements, there's going to be some small noise. Now, V might be very, very small. V could, in fact, be the error in simply calculating A times X in double precision, with double precision numbers. So V could be as small as round-off error in a numerical calculation. But generally speaking, this actually refers to some inversion, estimation, or reconstruction problem. It involves received signals or things like that. And V is simply, well, if these are sensor noises, errors, things like that. They could be errors because a sensor is only 14 bits. All that is lumped into this Y. So the real picture is Y equals AX plus V. Now you want to reconstruct X given Y. If there were no V, you can reconstruct it exactly if A is full rank and skinny. Exactly. But in fact, now there's an error. And in fact, now I'll tell you the sad news. You cannot reconstruct X exactly if there's noise. I mean, that's kind of obvious, right? So you have to make some prior assumptions about what V is. You have to make some prior assumptions about it. And then actually, you're not going to simply get an X that exactly, well, you don't know what V is. If you knew what V is, you could subtract it from Y, and you're back in the other case again. So if you don't know what V is, then you have no choice but to do something like best effort here. And the best effort is going to be, well, we'll see, is least squares estimation. Okay. So least squares estimation says this. You choose X hat, that's sort of that's your guess as to what X is, by choosing X hat to minimize norm of AX minus Y. Okay? And AX has a specific meaning. It is what you would observe if X were really X hat and there was no noise. Y is what you really observed. So you're basically getting the best match between what you would observe if the input were X hat, and what you did observe. So that's the picture. So so you minimize the mismatch between what you actually observed and what you predicted observed. Oh, by the way, in a lot of fields, A times X is sometimes referred to as the forward model. Okay, that's a good term. So it's the forward model, and basically it's something that maps X into ideally what you would get, what sensors you would see if your sensors were flawless and perfect. That's Y equals AX. So some people call that the forward model. By the way, it's a big deal. Somebody could work a couple of months to come up with some code that computes the forward model. Okay, and it simply maps X's into what you would observe. And it's a big task, I mean, depending on the particular problem, right? So it would be highly non-trivial, for example, to work out the forward model if the problem is a mechanical structure and the X's are loads that you put on it and the Y is a vector of 1,000 displacements. Okay, it would involve all sorts of finite element modeling, all sorts of stuff. You'd have to read in some description, some standard description of the structure and all this sort of stuff. So but for us, it's just AX. And that's called a forward model. So what this is doing is it says you get something which actually doesn't match anything in the forward model. And what you're doing is you're minimizing the mismatch between something that the forward model can give you and what you actually observed. So that's the picture. Now, what is it? It's nothing more than this. It says you take A transpose A inverse, A transpose, and that gives you your least squares estimate. Okay? Very simple. You'll see in a minute this works extremely well, does very, very clever stuff, all rather automatically. Something to mention here is the blue property. I guess some people call it, you also see it with BLU, but it's the best linear unbiased estimator. So let me explain that. Linear measurement of noise, so y equals AX plus B. A is full rank and skinny. And let's suppose you're going to look at a linear estimator. A linear estimator takes y, multiplies it by, in this case, a fat matrix B, and returns x hat. Okay, so that's a linear estimator. Okay, well you just multiply this out. This is x hat equals b times ax plus v. Have you turned on amplification in here? Because I'd like you to turn it off. Thanks. People in the back will let me know if you'll let. I presume you'll wave your arm. You'll gesticulate wildly. Maybe you didn't even hear that. In which case, the whole thing. Okay, I got the right sign. Good. Okay. Okay. So x hat is b times ax plus v here, and it's called unbiased if without noise, it's infallible. It always reconstructs x. So an estimator that works perfectly in the absence of noise is called unbiased here. Now what that means is this. If v is 0, it says x hat is bax. And the only way for x hat to equal x, always, is for ba to be I. Well, that means it's a left inverse. So by the way, when someone says left inverse to me, I think only of an unbiased estimator. That's what it is. That it is nothing more. To me, they are identical. A left, to see, if you see ba equals I, A is, well in that case A has to be skinny. If you see BA equals I, it means if A is sort of a measurement system, B is a perfect equalizer or a perfect reconstructor. That's what it is. Okay? Or an unbiased estimator. Now, if you have an unbiased estimator, then your error, that's x minus x hat, that's the error in your estimate, is x minus bax plus v. But BA is I. So this is x minus x goes away, and it's just this. So what happens if you have an unbiased linear estimator is that your error is now completely independent of what x is. Okay? And it depends only on b. And in fact, it's b minus b multiplied by this error. Now, what you want now is the following. Now you can see that not all left inverses are the same. Right? Because in fact, when one person has one left inverse, another has another, they both give you unbiased estimators. And by the way, if there's no noise, they will both reconstruct x perfectly. Now you introduce noise. When you put in noise, the two estimators differ if the two left inverses are different. And they differ because the error, the estimation error, is actually that matrix multiplied by v. So now you can see what you'd like. You really want a small left inverse. Okay? Now obviously, b can't be because then you could not possibly have BA equals I. So now you can see, if you want a small left inverse, and by the way, in this context, small means its error is not sensitive to the noise. That's what it means to be small in this case. Well, it turns out our friend, A transpose A inverse, A transpose is the smallest left inverse of A. In the following sense, if you take simply the entries of a matrix and think of them as a vector, then its norm squared would be sort of the sum of the squareds of the entries. And so it says that our friend, the pseudo-inverse, is the smallest in the sense of sum of squares, left inverse of A. And this is not too hard to show, but I'm not going to do it. And so people say then that the least squares provides the best linear unbiased estimator. Okay. I should mention one other thing. So far, everything we're going to talk about, when we talk about estimation, we don't do it in a statistical framework because for some reason long ago, it was determined that probability was not a prerequisite for this class. I'm not sure why, but that's the way it is, and it seems okay. I should mention that, of course, estimation, obviously, should be looked at from a statistical point of view. In which case, you know, after weeks and weeks of discussion of probability and so on, and statistics, you'll come up with things just like the things you'll say, like least squares. And someone will say least squares, and you'll say, what's that? Oh, I'm really doing maximum likelihood estimation with a Gaussian noise model, for example. That's what least squares would be. So I just wanted to mention, but that's always the way things are. Something that's a good idea can usually be very well justified by several completely different methods. So you'll also see this in statistics, but with completely different discussion all around it. So, okay. And it's not bad to know that ideas like least squares, although they are deeply statistical, you can also understand them completely and be absolutely effective in using them without knowing statistics. That was not a recommendation to not learn statistics, by the way, just for the record. Okay, so let's look at a simple example and let's just see what this does. So this is navigation from range measurements. And it's distant beacon, so we're going to use the linearized measurements. Now what that means is you actually take each measurement is an inner product along this normal vector pointing from the unknown position to the beacon. Okay, so this guy simply measures not circles, but in fact height, planes like this, lines, I guess in R2, like that's what it measures. You get this distance. Okay. Now the linearization is quite good, and so what you're going to get is this. You're going to get four measurements of x, linear measurements. So that's a 4×2 matrix, and there'll be a noise here. Now here, these noises. I mean, I chose a specific noise here, and the noise I chose from a random distribution. Again, this is totally irrelevant. But let's just give a rough idea of what it is. The noises are independent Gaussian. They have a standard deviation of 2. This is totally unimportant. What it means is that these V's, the entries, are off typically by ±2. They can easily be off by ±4. But it's very unlikely they're off by ±6. Okay, and essentially impossible that they're off by ±8 or something like that. Just to give you a rough idea, that's noise. And if you like to think of that, what it really means is that each of these measurements is something like a you could say a ±4, let's make them meters. It's a ±4 meter accuracy measurement. Okay, so that's if you want to get a rough idea of what these are. So what you'd say here is that what you're going to get is you're going to get the range to 4 beacon. You're going to get 4 ranges, measurements of the range, but each range has an error of about ±3, ±4 meters, something like that. Just roughly, that's the idea. So for example, if the real range is 10,000, blah, 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 you could easily have 10,000 plus 2, or 10,000 minus 3. Okay. Given those 4 noise-corrupted measurements, what you want to do is estimate the position. Okay? Now, here you got 4 measurements. You have 2 unknowns to do. So, I mean, the quick arithmetic tells you right away, just the quick accounting says you got about a 2-to-1 measurement to parameter redundancy ratio. That's good. It's better than the other way around, which is a 1-to-2. So you have 2-to-1 measurement redundancy, just roughly. Now, the actual position happens to be this. We just generated it randomly. There it is. And the measurement you get is this. Okay? Now, by the way, there is no x that actually will give you, if you plug in 2 numbers here, multiplied by these 4 vectors, you will not get these numbers. These are inconsistent measurements. Why? Well, because there's noise. In fact, we can probably get a rough idea of how inconsistent they're. They're probably inconsistent in each entry by about 2 or 3 or something like that, because that's how the noise was generated. Okay? Now we're going to do 2 things. The first one is this. We're going to take someone who took a linear algebra class. The class didn't go far enough. They didn't talk about non-square matrices. They only got to inverses and things like that, but they didn't talk about left inverses and things, or least squares. And so they say, look, I don't know what you're talking about here. I never learned about tall matrices. We did square matrices. And we learned that if you have two things you want to find, two measurements does the trick, and you get a 2 by 2 matrix. And I even know the formula for the 2 by 2 inverse, or something like that. So one method to do here is to simply ignore the third and fourth range estimates. Okay? So this is the just enough measurements method. You got two things to measure, you take two measurements. And I mean, without noise, that certainly is it's gonna do the trick, assuming your two measurements are independent. Okay? Well, what that corresponds to is taking the top half of this matrix and inverting it. Because if you have, I mean, that's how you get X. And that would actually exactly reconstruct X if there's no noise. So in fact, this method of sort of inverting the top half and padding it out with zeros, this creates a left inverse. You can check, well, I didn't give you A. But had I given you A, you could multiply this thing by A and you would get the identity. It's a left inverse. And a left inverse means this. It will reconstruct perfectly if there's no noise. That's what this does. By the way, when you see a matrix like that, let's call that B, whatever, just enough measurements. I should maybe call that B just enough measurements, like that. If we write this out, if you see this 2 by 4 matrix and I say this matrix maps range estimates into it maps range measurements into position estimates. Okay? When you see this and you see these zeros, you should immediately come up with an explanation. And in this case, what is the meaning of these 4 zeros? It means the last two measurements are irrelevant. Okay? This 0 is sort of just an accident. It's an accident, and it just means, to the precision I'm printing these, which is not exactly high precision, it says to the precision, it says that basically our estimate of X, well, let's say it right. Our X1 hat doesn't depend on Y1. Did I say that correctly? I think I did. And by the way, you could probably look back at the geometry and figure out why that's the case. Well, I'm not going to worry about it, but that's it. Okay. All right. So here, the norm of the error is 3.07. We should give the RMS error, so you should divide by square root 2. So 3 divided by 1.4, I don't know. What's that? So you get an error of about 2 in each. I'm getting the RMS error here. So you get an error of about 2. And by the way, if someone says, hey, you're off by 2, they'd say, pardon me, your range measurements are off by about 2. Does it sound reasonable? I mean, that would be the response if you use this method. They're off by about 2 in both X and Y, but the measurements were off by about 2, so who can blame the person? Okay, let's look at the least squares method. When you work out A transpose A inverse A transpose, you get this matrix here. Okay? And the first, you see a lot of things about it. Let's talk about some of the things you see about it. Oh, by the way, the estimate it produces of 4.95 and 10.26, the norm of the error is 0.72. You divide by 1.4, and you have a norm of error which is about 0.5. Okay? So the first thing you know is, at least for this one random sample I generated, this thing did a lot better. It did a lot better. Okay? So that's the first thing you notice. Now this is another left inverse, and in fact, it's interesting to compare the two left inverses. Let's compare these two. So let's just look at these two left inverses. This one we already said, these zeros means that you don't, this estimator doesn't use the second two measurements. It doesn't use the last three, the third and fourth range measurement. You know, what you see here is that all these numbers are kind of on the same, I mean, they're all there. They're smaller than these. You don't get numbers as high as 1 and -1. But they're all kind of, you're using everything. By the way, there's a name for this. It's sometimes called, actually this is called sensor blending. That's what's actually happening. Or fusion, that's a beautiful name. People talk about sensor fusion. And so if someone said, what have you done here? And you don't want to say, no, it's just least squares. If you want to impress the person, you say, I've implemented a sophisticated sensor fusion algorithm. So that would be the correct way to say this. And they'd say, does that mean? And you go, well, as you can see, I'm blending all 4 measurements to get each estimate in just the right proportions. And you'd say, well, how did you get these? And you go, it was tough. It was really tough. Anyway. But the idea remains that this is one of the ideas you see in, you laugh, but I mean, there's whole fields where people don't even have a clue about these ideas, right? Where you get a lot of data, a bunch of data, and you want to make some estimate of something. And there's just totally straightforward ways to do that like this. But they're simple. They're 3 ASCII characters. This is like A\Y or something like that. But the point is, it's actually doing something quite sophisticated. It's kind of blending all these things the right way. Okay, so that's the first thing you say. I want to ask you a question, though. Obviously, for this one instance, this estimate was a whole lot better than this one. Okay? But I have a question for you. Could you please tell me a situation in which this estimator will outperform this one? And in fact, let's make it simple. I want it to outperform it by a lot. Having just made fun of this estimator, I would like you to explain a situation in which this estimator outperforms this one. What is it?
If you would just randomly have a whole lot of noise on the 3rd and 4th sensor and
there you go. Perfect description. Okay, so I'll repeat it. It goes like this. Suppose, I mean, the one thing you can say about this one compared to this one is it doesn't use the last 2 measurements here. So if those last 2 measurements were way off, in fact, suppose you were being spoofed, for example, or suppose the sensors the range sensors got totally wacky, dropped a bit somewhere, and they were way off, way off. This one is completely insensitive to the errors in the last 2 measurements. This one, however, if you're way off in Y3, if V3 or V4 is really big, you're in big trouble because of this. Okay? So it's not that simple to say that this is always a better estimator than this one. And indeed, there are cases where it might not be. But the point is that generally speaking, if what you can say about the V's is that they're all small, they're all about on the same order of magnitude, this is very likely to be a lot better than that. Okay, so that's the picture. Now we can go back and we can actually do our example from the first lecture, which is this. You had an input that was piecewise constant for periods of a second, or a nanosecond or microsecond if you like to make a different time scale, but it doesn't matter. It goes into a filter, and that simply means that this signal here is a convolution of that input here with a convolution kernel or impulse response. You sample that at 10 hertz. That means you sample it, every 100 milliseconds. You get this. And then, now comes the part that's tricky. We actually subject that to 3-bit quantization. And the formula for that is this. So the quantizer characteristic is this. And this basically selects the nearest of 8 levels spread over the interval -1, 1. So that's what this formula does. Okay? And so here's the picture. Here's the input signal that we don't know. It might have been, for example, a coded communication signal being sent to us. Here's the step response. This convolved with the derivative of this, that's the impulse response, gives you this. And you can see that it's kind of smooth, but it kind of tracks it. I mean, here you can see sort of where this dips down. You see a dip here. It's delayed on the order of 1 second. And you can see sort of where this goes up. There's a bump. It's smoothed out though, like that. So it's delayed a half a second or something like that, and smooth. And then this is what it looks like when you severely quantize it. Okay, 3 bits. And the idea is, given this, estimate that. Now, by the way, looking at it by your eye, I think the answer would be forget it. It's not going to work. It's already hard enough here because this thing kind of all smeared around. In other words, this point here is produced not just by what's in this interval, but what's here, 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 and so on. Okay? So you just say forget it. It's all mixed together. Can't do it. And then when you quantize it, it gets even sillier. It seems sillier. So we'll just write as y equals ax plus v, where a is an r 100 by 10, and aij is this, and you can just work out the details. This is how you map x into y. Then we'll take v here in our model of y equals ax plus v is going to be the quantization error. It's the difference between y tilde and the quantized version. And by the way, that's a vector. It's actually very complicated. It's a deterministic function of y tilde. But I can tell you one thing about it. All of its entries are between plus minus 0.125. Because the width of an LSB here is 0.25, a least significant bit. And so the error is no more than 0.125. And the least squares estimate is this. And you can see that it pretty much nails it. Or at least it gets very close. In fact, oddly, it gets closer. It gets twice as accurate as the quality of your A to D. Okay? I tried to shock you with this the first day, and I remember you were like, that's cool. So, you know, you should be impressed by it. So that's the idea. By the way, this example is a perfect example of how all of this actually is used and how it goes down in practice. No one will bump into you later tonight and say, oh, quick, I need help. What is it? I've got this matrix A, and I've got this vector y, and I need to find x so that norm ax minus y is minimized. Can you help me? No one is going to do that. What will happen is you will go back to some lab or something like that, or go off at some company, and someone will give you they'll give you, except it won't be clean like I made it. They'll throw some huge thing down, and they'll be, if it's communications, there'll be acronyms flying all over the place, and they'll say, yeah, we're using, you know, 4QAM and this and blah, blah, blah. And it'll go on and on and on. Oh, and you should use the such and such model, and there's this, and there'll be some finite elements and PDEs thrown in. Horrible thing. And what you will need to do, nowhere will they say least squares. They will certainly not say linear algebra. They probably don't even know linear algebra. They won't say it. They'll have all sorts of things. They'll talk about, you know, I don't know, who knows what. There'll be spherical harmonics and cosines and sines and different coordinate systems. And your job will be to just sit there very calmly, read the pile of stuff, go read a couple of books on the field, and sit there and realize I will write all of this as y equals ax plus v. And then you will go to your computer and you will type a\y. Very calmly, very calmly. So the last part will will be very fast, but the first part is all the work. So, okay. So I'm just saying this example is a good one. This is exactly how it happens. There's block diagrams and all sorts of transfer functions and all sorts of nonsense all around, and it's your job to, you know, get rid of all the field-specific details and abstract it away in something that fits this way. Okay, so that's it. Actually, I want to show you one thing here. In this case, I just selected a couple of rows of A transpose A inverse A transpose. Now, what this is this is really cool. What this does is this thing maps Y. That is this smeared quantized received signal. This maps the smeared quantized received signal into our estimate for these 10 real numbers, the 10 real numbers in the original signal, x1 through x10. That is a 10 by 100 matrix, okay? It maps quantized, smeared, received signals into estimates of x1 through x10. I have plotted here row 2, row 5, and row 8. These have a meaning. Row 2 of that matrix actually shows you how those 100 received signals get multiplied to create your estimate of x2. So when you take an inner product of your 100 received signals with this vector, that's forming this unusually good estimate of what x2 is. You look at it and you'll see some really cool stuff. If you look at this, you will see this says that to get the estimate of x2 here, it really says, in fact, let me ask you, it says that the quantized signal from 6 seconds to 10 is pretty much not used. Why am I saying that? Because these entries of B are small. You see what I'm saying? That makes perfect sense if you think about it. Because you know that the smearing is kind of local in time. It says that actually to get a good estimate of x2, it says you really kind of, the most important thing is actually y right at time 2. By the way, x2, for the record, is actually not there. x2, this value, is at 1 point, it's sort of the middle, is 1.5 seconds. So this thing was smart enough to realize, very roughly, that you should sort of sample 1/2 second late. Why? Because that's roughly what that smearing did. It added a 1/2 second delay. Okay? So I'm just saying that's what this shows. This little negative bit here, that's cool. That's actually what in communications is called equalization. And it basically says you should sort of subtract from what you see here, this thing, because this thing was kind of corrupting your measurement. And so if you subtract for it, you're actually kind of compensating for it. So this is equalization. So, okay. Oh, by the way, this is the third part of how this goes down in practice. So the first part, we already talked about the first part. The first part is is decoding all these stupid books and the silly field-specific notation. That's the first part. The second part, which finishes when you put it in the form something like y equals ax plus v. The second part is a backslash v, the a backslash y, that goes right away. Now the third part is now to explain is to go back and explain your estimate to people who have never heard of pseudo-inverses. So you know when if you say it's just least squares and they're okay, that's fine. But sometimes they'll just look at you and they'll say, "What's that?" This means you have to explain it, and then you'd plot these pictures and you'd give this story until they go away. And you'd say, you see, this is how I estimate the second one. This is how I estimate row 5. I mean, truly, what's really estimated, of course, is A transpose A inverse A transpose. But at least this makes the story clear. And by the way, you could even do things like now truncate this, and now have sort of a finite equalizer if they were uncomfortable about your estimating using material stuff from the future and stuff like that. So that's the idea. Okay. Any questions about this? And you're still not impressed with this. I can tell. I've been doing this for a while. I can tell when people are impressed and not impressed. Fine. It's just fine. Okay. We'll look at some more applications. And the first one is data fitting. So this is very famous. You're given some functions on a set S. S could be anything. It actually could be finite. It could be R. It could be an interval. It could be multidimensional, like it could be R3 into R. And these are called regressors or basis functions. It's called basis functions even if they're not independent, but we'll leave that alone. Okay? So you have a bunch of functions here from S into R. And you have some measurements. Now a measurement looks like this. By the way, some people call them samples. That's another name for it. So the other one is you have measurements or samples. And a sample is a pair SI and GI. Okay? So that's a sample. And so, for example, let's make this specific. Let's let S be R3 or R2. Let's make it simple. In fact, let's make S 0, 1 cross 0, 1. That's the unit square. It's something that looks like that. And so a function, one of these functions, a basis function here, is a function from this unit square to R. Okay? And so, for example, I'll tell you, F1 is just the constant 1. F2 is and I'm going to interpret, let's put a physical interpretation here. That's the temperature at a position on a square plate. Okay? That's what it is. That's the meaning of this. Okay? So each of these basis functions is now a temperature distribution. So the first one is just flat uniform distribution 1. The next one is like, let's say, an x gradient. That means it's something where as you move across here, the temperature grows linearly. F3 is going to be a horizontal gradient. Okay? F4 is some weird thing, I don't know who, it depends on the field, right? In fact, these things come from the field. So you go to the person, let's say it's Bob. They're usually called Bob, who've been doing this for a long time. And Bob says, no, you should use the spherical Laguerre harmonics of the 12th order. We've been doing this for years. Trust me. And you're like, okay, whatever. So anyway, that's usually where these come from. Or they might come from something, some other place. Okay. For example, you might say, oh, no, it's heat equation, blah, blah, blah. That's Poisson equation. You know what? These should be the eigenfunctions of the heat kernel. And so these should be the cosines and sines. Okay, and this is actually a Fourier series. Okay, so it just depends. So you're given measurements. That means that you sample the temperature at some of these points. And what you want to do is you're going to form a temperature distribution, which is a linear combination of these temperatures in such a way that it matches approximately your measurements. Okay? Now here, we'll talk about the other regime, but in this case, we're going to assume you have a lot of measurements and not that many bases. So I have 6 bases. In fact, that's kind of the point of having a well-chosen basis, is that if you have a well-chosen basis, you can actually describe all the temperature distributions that you're likely to actually see in practice quite well as a linear combination of, let's say, 8 basis elements. Okay? Now you take 1,000 measurements of the temperature. You sample the measurement 1,000 places. Well, you only got 6 numbers to choose, and you have 1,000 measurements. So a least squares fit does this. It says, let's choose these coefficients, the x1 through xn. By the way, in this context, these are often called, I mean, not that it makes any difference, something like a1 through an, because, well, I'm using x because it's going to end up as x when we write norm y minus ax. But in fact, normally it would be called alpha. Oh, and by the way, often these coefficients, to make it really complicated for you, these things are actually very often indexed not simply from 1 to n, but by multiple complex indices. So for example, if you're doing image processing, these might be the such and such, wavelets, or the edgelet. These might be the edgelet series, and they might have like 3 indices. This is just to mess you up, okay? So, but we just enumerate them as 1 through n, and your job is to choose those coefficients like this to make this thing small, to get a good fit. Well, once again, I'm not going to do it, but you look at this and you just take a deep breath. And remember, they won't do this. They'll index these horribly. They'll give you 40 papers on edgelets and the wavelet transforms. They say, oh, you don't know about wavelets? Well, where were you? And they'll throw you a bunch of papers at you and walk away. And so these x's will be called alphas, and they'll be like, let's say, have 2 indices in the superscript and 2 as subscripts. Okay? And it'll be hideous. Okay, your job is just to convert this very calmly to this, to just ax minus g. And aij here is nothing but fj of si. So that's it. And you just work that out because you just realize that is ax. This is axi. And that means that that's actually giving you the ith row. And so, in fact, it's nothing but this. So it's extremely straightforward. It's just this thing. Okay. So the least squares fit here is A transpose A inverse A transpose G. You just work it out. And the corresponding fit is this. So this would give you your fit. And this has a lot of uses. Already. And let me just say what some of them are. But mostly what it is it's a very good way to develop a simple approximate model of data. Okay? And let me give you, I'll just make up some examples and you'll get the idea. When you have a simple model, you can do things like interpolation. You can say, I'm measuring the temperature on this core at 75 places. But I'm really interested in what the temperature is, very likely, at these 22 other places. I couldn't get a sensor in there. What is it? You study the thermodynamics and somebody tells you, well, actually, here's a good basis, the spherical prolate, the prolate spherical, something harmonics. And you go, whatever, okay? So you get 30 of these or 20 of these or whatever the appropriate number is. And you now fit the data you have to those. Now you have a model. That's your least squares fit. You can now make a guess as to what the temperature would be anywhere on that plate. Are you right? Who knows? It depends on whether your basis, whether in fact the real temperature distribution is in the range of the basis. It probably isn't. So as to whether or not this is whether you get a good estimate, a good interpolation or extrapolation for that matter here, depends on the quality of the basis chosen. But the point is it gives you a very good method to do it. By the way, these methods will work very well if they're done responsibly. You can also do smoothing of data. So that's one of the other things that happens is if you have the data has lots and lots of noise, but you have a lot of it. and you fit it, you're actually going to get a nice smooth thing that will actually, so you can use it as a method to denoise measurements that way. You can even go back and actually, if you think of, let's say, GI as an extremely noisy measurement of what some underlying f of SI should be, you can actually first do the fit, then come back and look at FLS fit of SI, and you say, you know what this is? I believe that's really what this is. This is just the horrible noisy measurement. And now you've got a beautiful way to denoise the data. I'm just making up applications because there's lots of them. I'll give you one more. So here's a real application. Actually, all of the ones I talked about were real, but I mean, here's one. You're developing an aero model of some vehicle. Okay? So finally you do all the computational fluid dynamics, all this stuff. Finally, you take the stupid thing down to NASA or whatever, NASA Ames, and you stick it in a wind tunnel. This is very, very expensive. Okay? And you actually take a whole bunch, you fire the whole thing up and you take a bunch of data and you tilt it up and you do all sorts of things and you change the speed of the thing and you measure, you take thousands of measurements of the moment and the force put on that structure, on that vehicle, as a function of, for example, its angle of attack, its various other angles. So you got maybe 3-4 dimensions there, and the speed of the fluid it's moving in. Everybody see what I'm saying? Is unbelievably expensive. You take 1 million measurements because you just take it continuously and so on. That's what you do. Now you want to come back and you want to just make a simple simulator for this vehicle. Well, you need at some point, I mean, basically it looks like this. It looks like x naught equals f of x. There's some other stuff in there, but this is this function you just took samples of. Okay? So what you do now is this. You don't have f. You just don't have it. What you have is you have 1 million samples of f from your wind tunnel tests. Here's what you do. You do have a very good idea of what f should look like, because otherwise you shouldn't have put the thing in the wind tunnel. So you clearly had some idea, and everyone knows roughly what this looks like. I mean, the first derivatives, you know what those are. Those have they have well-known names in like arrow and stuff like that. They're the stability derivatives or whatever they call it. You know roughly what those are. But so actually you can figure out a very good basis for these. You know, for example, about the phenomenon of stall. You know that if the angle of attack gets too high, your lift is going to precipitously drop. So you know all these things because you've done those. So you can come up with a very appropriate basis. You now take that 1 million data points and you fit an approximate f. By the way, that wouldn't take so long. Just if you're curious how long it takes to do a least squares with 1 million variables, it doesn't take that long. But in any case, let's say it takes 10 seconds or something. It wouldn't even take that. But let's suppose it takes 10 seconds, or it doesn't really matter what it takes. You do that. You know what you have now? You now have a very small piece of code, a little like one screen of C or something like that, that will evaluate an approximation of f in well under a microsecond. Everybody see what I'm saying here? So you just took 10 million pieces of data and you scrunched it down, you fit some data, and you now have an approximation. It's an approximation of f, but a good one, and it's just 50 lines of C. Okay? You can evaluate it way under a microsecond. You know what that means? It means you can simulate this thing like crazy now. Because in a simulator, you're going to call that every time step. And you're going to call it tens of thousands of times. I get the feeling that no one has any idea what I'm talking about. Did any of that make any sense? A few people. They're just being polite. They're the ones in the front. Okay, so that's the basic idea. We'll look at a quick example, and then we'll quit for today. So least squares polynomial fitting. I mean, this is very, very famous. You want to fit a polynomial of degree less than n. So your coefficients are a0 up to an minus 1. The basis functions are, of course, just t to the powers of t. By the way, that's a very poor choice of basis functions. I'll tell you why next time. Unless the data happens to be between, for example, remarkably, the t's happen to be between -1 and 1. Even then, it's a poor choice. And this matrix A has this form, which is a Vandermonde matrix. Okay? So it's got the rows are increasing powers. And I won't go through this, but we'll just look at a quick example. Here's a function, which is by no means a polynomial. I just made it up. It's some stupid rational function. And we take 100 points, and we'll do least squares fit for degrees 1, 2, 3, and 4. And we'll just take a look at what happens. Now, a degree 1 polynomial, that's a line. This thing has almost zero slope, but not quite. And this is the fit to this function of degree 1. And you can see it's trading off the underestimate here with the overestimate here. Because it's a line, it can't do very much. Here's the quadratic fit. And you can see it kind of got a bunch of the curvature here a bit. That's the dashed one is the curvature. So it kind of got some curvature. Here's the cubic fit. And notice you're already getting a pretty good estimate here. The cubic allowed you to put this little fit this little wiggle, get the tail over here. And here's your quartic. Okay, so and these were all just done least squares, something like that. Okay, so we'll quit here.